purpose of our company is to make a good use of these byproducts and resolve the nuclear waste issue. There is direct generation of electricity, heat, we can convert that and so on. You're very right, it's already being used. It's the matter of how we can make them more advanced.
This is EnergyCast, and I'm Jay Downhauer. Today we're talking about nuclear batteries, how one technology could change how we think about energy on the go. The concept has been explored before, putting radioactive materials to work to heat or power equipment. My guest says a version of their technology is currently powering the latest Mars rover, and thanks to that versatility, will roam the red sands for years. I was first introduced to this concept after my conversation with Curio's Ed McGuinness, who I recently spoke to in episode 134. If you heard it, you may have picked up on this line.
We're already talking to some transformational battery companies that are looking at potentially using this heat and using it as a battery and converting into electricity for microelectronics and other things, such as your phone.
From there, a simple web search revealed the work today's guest is doing. Like Ed said, they're using the fission products, are one of dozens of radioisotopes left over from spent nuclear processes. This is the material we'd still find ourselves with if the United States ever recycled their nuclear fuel. It makes up about 4% of the 86 metric tons of spent nuclear fuel American power plants have generated so far, or 3.5 tons. Now, it doesn't seem like much, but my guest says this is an incredible amount of energy. What they're developing is essentially a power source and a battery rolled into one. He compares the nuclear material to the sun and their semiconductor to a solar cell. The radioactive decay energizes the cell and voila, energy. Oh, and one more thing. These isotopes are dispersed and encased in synthetic diamonds. Ladies and gentlemen, Shirley Bassey.
Diamonds are forever.
Some of these diamonds would literally last forever. And while some isotopes from fission products can only last a few days, some others like carbon-14 can last millennia. So you could have batteries that could long outlast whatever they're powering. And the use cases, as my guest describes, are essentially everything. Home electronics, your phone, electric vehicles, even commercial energy production and space travel. As you might imagine, we discuss safety considerably in this episode. Who wants to have a cell phone powered by decaying radioactive material, even if it does never lose its charge? My guest says they believe they've built in protections to keep the bad stuff inside the batteries. They've also deposited the material within the cell so that there's no way to really crack open the battery and use that material for mischief. If the public can accept the enormous benefits of self-powering batteries like these, and if nuclear recycling can become more widespread, we could see a rich energy future filled with these durable diamonds. My guest today is Dr. Nima Golsharifi, CEO of NDB, a nuclear battery developer based in San Francisco. NDB is short for Nano Diamond Battery. Nima and his colleagues founded the company in 2019. Since then, they've received a number of prizes and support from the nuclear community, as it would seem, since they appear to have the answer about what to do with the rest of the material in the nuclear supply chain. I reached out to Nima and his team shortly after my Curio interview. We cover all the issues you'd expect from a near-exhaustible battery that harnesses decaying nuclear material. He was kind enough to give me some time recently from London. I hope you enjoy my conversation with Nima Golsharifi. We're here with Nima Gul-Sharifi, CEO of NDB. And Nima, I was drawn to this technology after talking to Ed McGinnis at Curio a few months ago. He said not only can you recycle most of the spent nuclear fuel, the leftover fission products, I'm doing quotes with my fingers, can make what you are developing. So I'm considering this a continuation of that discussion. Why don't you tell us what Ed was talking about there?
Ed was very right. Spent nuclear fuel or nuclear waste is mixed up with short-lived fission products and isotopes heavier than uranium, which are called transuranic isotopes. These have intermediate half-lives of tens of thousands of years and require geologic storage for hundreds of millennia. When spent nuclear fuel exits in the reactor, these bundles are placed in a cooling pond for several years before being transferred to dry cask. And basically, failure of government policy on Yucca Mountain has stranded more than 85,000 metric tons of these spent nuclear fuels in America. And taxpayers have already paid over $50 billion if the state of affairs don't change. So simply what I can say is that NDB Solutions and the purpose of our company is to make a good use of these byproducts and resolve the nuclear waste issue, and in turn help the environment by promoting the nuclear energy, which is a clean source, and in turn supporting the society by creating a type of circular economy.
Yeah, there's a lot of hurdles before a domestic nuclear fuel recycling facility can be built. I take it you'd initially try to get fission products from one of the other facilities around the world. There's one in France and in Japan. Where are you getting your feedstock initially?
Yes, in addition to nuclear waste management companies and the reactors themselves, there are different organizations that can supply. Some of these names might be familiar. You mentioned some of them, like Orano, which we have been the grand winner of their challenge, or National Isotope Development Center in USA, or Oak Ridge National Laboratory, and so on. These are very good sources for radioisotopes at this stage of time.
Yeah, Nima, say we did use up all the fission products from spent nuclear fuel in the United States. Ed said that there were 86,000 tons of spent nuclear fuel from our nation's nuclear power plants. So that works out to about 3.5 tons, if I'm doing the calculation right, about 4%. Is that the number you got, about 3.5 tons in the United States?
Yeah, it's quite right number.
Yeah. How much energy is that? What would 3.5 tons of fission products do as far as batteries?
Interesting question and calculations, but let me say that the specific energy of the spent nuclear fuel and the fission products are function of time and depends on multiple factors, including density and concentration of fission products. Also, it is dependent on the operational conditions of the used nuclear fuel, such as burn-up ratio, the fuel type. Let's say, to simplify this, if we just consider one type of these nuclear spent fuel waste, from the top of my head, the approximated specific energy for these 3.5 tons of fission products would be in order of 10 quadrillion of joules. So these values show how alternative sources of energy, such as radioisotopes, can play an important role in sustainability with their extremely high specific energy in comparison to electrochemical batteries or fossil fuel powered engines.
I think what we can say from that is a lot of energy. So even 4%, right? So getting into the battery science, this is different from a chemical battery, lithium ion. That's stored chemical energy, but this is a radioactive isotope that is powering the battery, correct?
Yeah, this is a different technology. So speaking metaphorically, it's similar to solar panels, with the difference that NDB generates electricity using the radiation from radioactive materials instead of the sunlight. At the same time as chemical batteries do, the NDB will be able to store the excess charge in a storage device. And in this way, we took the features of chemical battery and the solar cell to combine them and create this NDB.
You're saying there's more of a conventional battery storing whatever the radioactive isotope is giving out. It's not directly powering whatever device this battery is powering. There's an intermediary, right?
Think about solar panels, yeah? They can power up directly or they can use the storage devices, correct? It's quite the same thing over here. So when you are thinking of our technology, you have to really think of how solar panels and photovoltaics are working. And then instead of sunlight, we are using the radiation from these radioisotopes.
It's kind of self-charging. Yeah, it's like a battery that has its own charger on board with it. Is that a way to think of it?
Correct. That's right.
You say you're encasing the nuclear material into quote unquote diamond. We know there are synthetic diamonds. Is this expensive? Is there a way to mass produce this if all you're doing is shielding the isotope?
Yeah, developments in CVD technology have greatly reduced the cost of synthetic diamonds. CVD is chemical vapor deposition technology. It's used in semiconductor industry mainly. The cost of manufacturing these synthetic diamonds did fall from $2.4 million per kilogram to something around $40,000 per kilogram in 2018. And as technology moves towards bulk manufacturing, which is not there yet, further improvements are expected and costs could decrease, I hope, in the near future. Of course, you mentioned diamond, which is a great semiconductor, and I can say it's the most efficient one. But our designs are also based on silicon carbide and liquid semiconductors as well.
You're suggesting these batteries can be used from everything from a cell phone to electric vehicles. How close is this to being competitive with something like lithium? Let's just start with price.
Yeah, so price at the moment will be higher than lithium-ion batteries, yeah. But by the time where there is mass production or reactors, Ed mentioned that in the previous meeting, comes up and the fission products become cheaper, it becomes very, very competitive, and I can say maybe better pricing than lithium-ion batteries. So it's a matter of time, a matter of production, and the offtake that can happen over the time. About the use case, because it's quite important to have wider use case for these batteries, and then based on that, you can mass produce at scale, the economy is going to change. So the use case would be basically whatever device that requires electricity. Our solutions could potentially be applicable for low, medium, and high power. If we succeed the scope, we will be quite wide with the applications, starting from common devices we use in everyday life at home to industries or even space and future space colonies if there will be any.
Let's talk about safety, because that would be the thing that people would be concerned about, right? There was news a couple years ago about this idea of holding just a normal cell phone next to your ear and some of the safety concerns there. I'm wondering how you're able to handle the messaging of having a battery powered by something like this and hold it up to your head. So how can you, I guess, calm people's fears about something like that?
Yeah, you're very right. In general, the word nuclear or radioactive may sound very scary, as some people may be reminded of what you have mentioned, or even nuclear bombs or Chernobyl disaster and so on that we hear. But let's be honest, not many people know that most smoke detectors contain radioactive material, and still they have them at home without any problem. I think we have to explain and educate public about merits and potentials. And I think it can be initiated by media like yours, and then gradually building a profound sound. In case of ours, well, the design is quite confined to making sure that radiation cannot escape the device itself. And in terms of the type of design we have, when it comes to specifically casing, we have a transducer locking system, which prevents the isotope from being accessed in bulk and being used for purpose other than the NDB power source. We specifically do this by nanoscale ion implantation of radioisotopes within our structure, and this allows us to meet various consumer safety requirements.
This is what I'm getting fascinated by, is this idea of how much of the fission product needs to be in each battery. Let's just say you have an electric vehicle. You have a battery that's sized for the vehicle. The fission product, is there enough of it in the battery for the electric vehicle to let the vehicle run indefinitely? Or do you undersize it knowing that you are not going to be running it 100% of the time? Because you're talking about two different things, right? You're talking about the isotope being able to power a battery, and then the battery is then powering the device.
Yeah. So it's a very interesting question, actually. You touched a very important point. Let me clarify. There is an option of having a storage, and there is an option of not having a storage with our device. Yeah, it is acting like a generator, and if we can supply a constant amount of power that is required by the device, then there is no need to have a storage device. When it comes to electric vehicles, there are a few challenges. So one is the heat that will be generated by the radioisotope. We have to consider, when we are going to design a battery for electric vehicles, the type of radioisotope we are targeting is more dense and is highly energetic. So that means you're going to produce more heat. There should be a way to dissipate this heat, because if you leave the car for some time somewhere, there will be built up of this heat and the charge, and over time this will be converted to heat, and that would be a problem. So I think when it comes to the case of electric vehicles, there should be the correct infrastructure in place for the battery can be there. So it will be a matter of policies which can be assigned to it. I think electric vehicles is a matter of time for our type of technology. However, it can be there saying that we can answer these challenges. advantages. So let me give some examples about that. If you have a structure where electric vehicles have the option of self-drive, and let's say if any electric vehicle is sitting somewhere for a week or a month, it will automatically go to a bay or an area which can transfer the electricity back to the grid. Or let's say in any location that the cars can be parked, they can be connected to the grid, so they can sell the electricity that they are generating back to the grid while they are parking the car.
Okay, so fission materials right now is just regarded as a waste, but as time goes on and there's a very definite value here that can be harnessed, what's the price of fission materials now if you were to go out and buy it? And then what would be the price of it once it becomes more of a commodity?
Yeah, so I think this question should have been asked from Ed because they are the one who are working on it directly. But it depends on the fission product that you have, yeah. So if it's coming from nuclear waste, we are being paid to recycle this nuclear waste. And based on the data I had, it's something around $18,000 per cubic meter. But let's say that the nuclear waste is over and there is not much left. So production of these fission products is quite important. So at the moment, based on the type of isotopes, the cost varies and some of them are quite expensive. I think people can go to NIDC, the National Isotopes Development Center, and they can see the prices as well. They exist over there. However, with the new type of reactors and thorium-based reactors, this is going to change and the prices are going to change. And there are a range of possibilities which will be open to the market.
You know, Nima, I'm also wondering, you got something that essentially can generate unlimited energy, right? Has there been any thoughts about maybe not even messing around with batteries at all, just creating an electric generator and then selling that electricity onto the grid?
Yes, actually, we are working on that. And that's the area which is a high power application.
Yeah, so a little bit of everything. Back to the safety question real quick. Say someone cuts the diamond casing and tries to get the nuclear material out. What happens? How much nuclear material is there?
It depends on application and the amount of power we're going to take and the type of isotope over there. But basically, I can say because we have ion implanted the radioisotopes within the structure, they are distributed in nanoscale. It's almost impossible to have access to the material in a bulk. That's the way our design is. And I can say it's very safe in that way.
The toughest question is probably, what is the appetite for this? It's amazing, but nuclear fuel has a bad rap. Again, going back into the safety and some of these other things, but a lot of upside too, right?
Yeah. But there is another thing. We get a lot of positive vibes and support from the people themselves. So we have to be understanding where this bad vibe is coming from, because I see so many people pro-nuclear and pro what we are doing as well. But again, I think it's a matter of education and educating the public about the potentials on how we can reduce the CO2 emission using nuclear energy, how cheap it could be, how different it is from other things, other type of energies. So I think it's mainly a matter of education and the support of policymakers in making such things possible in the world.
Nima, I think some people might say, well, isn't this proliferation, right? Or is there some sort of analog that we're dealing with right now? I think some people also say that there's radiation in your granite countertop.
So that is quite easy. You can measure the amount of radiation which is coming out of a device like ours. And then you can measure the radiation in your background, correct? And you can compare, and that will answer.
There are so many applications here. You're almost thinking this is an energy source, might be a waste on just an electric vehicle or your cell phone or something like that. So where do you think is the appropriate use for these kinds of batteries, these kinds of devices?
There are lots of use cases. There are a couple of areas which is very interesting to myself. One of IoT devices. I think there is a very large potential for such sensors and monitoring devices in very remote locations. There are a huge amount of applications in space electronics, which opens up new horizons over there for humanity and the future of humanity. And as an alternative source of energy at the moment, it could be quite profound and interesting. You mentioned transport. I can mention, in addition to that, consumer electronics. So consider if you have a mobile phone that doesn't run out of charge, or a laptop or so on, that can go without running out of the charge during your operations. In terms of drones, it would be very interesting application as well.
Yeah. And Nimi, I think this is clear on NDB's website, is the idea that you're seeing these as almost a generational resource, right? Like the batteries are going to outlive the users. Once the cell phone is discarded, once the electric vehicle is discarded, the batteries are going to be recovered and used again. Yeah.
Yeah. It depends on the radioisotope and the half-life of of that. So we have radioisotopes which have much shorter half-life. It would be a matter of days or matter of years, or even carbon-14 can go for 20,000 or more years. So it depends on the radioisotope. And what we do, we select the isotope based on the application and we design on that. So if it's a mobile phone, we usually try to find an isotope which matches the timeline that is required, which is usually about 2 years and so on. But generally speaking, during the lifetime of the device, it will not run out of charge.
Okay, so you have various lifespans for the batteries. That's interesting. A lot of people saw The Martian with Matt Damon, came out a couple of years ago. He was using a self-contained nuclear battery to stay alive in that movie. You mentioned this earlier. Obviously, there's potential here for space, the ideal solution for space, right?
Yeah, I can give one real-world example rather than sticking to the movies. If you consider Perseverance, the 2020 Mars rover, it runs on a so-called RTG, or the radioisotope thermoelectric generator, which is a nuclear battery converting the heat generated from plutonium to electricity, and it allows it to operate around 14 years. Our goal is to combine different modalities and make the technology more efficient. There is direct generation of electricity, there is heat that is being generated, we can convert that and so on. You're very right, it's already being used. It's the matter of how we can make them more advanced.
Absolutely. Well, this is so exciting, and I can't wait to see where this all leads. All right, Nima, I'm going to finish with a lightning round of your thoughts on different energy technologies, starting with natural gas.
Strong future, but a finite source.
Crude oil.
Should be used for plastics rather than being consumed.
Nuclear.
Clean and cheap.
Coal. I'll add coal with carbon capture.
Yes, CO2 emission.
Wind.
It's not always windy.
Solar.
Intermittency.
Biofuels.
Shortage of food and water.
Hydroelectric.
Environmental impact on the fishes.
Geothermal.
Location specific.
Energy storage. You guys.
Deep decarbonization of electricity systems.
Energy efficiency.
Policymakers undervalue that.
And then finally, fusion power.
It's the future. I can go more than 3 words on this if you want. It's a very interesting topic.
No, I'm going to hold you up as the example because sometimes the lightning round will be as long as the interview. All right, Nima Golsharifi, NDB, thank you so much for your time.
Thank you. Thank you for your time. And it was a pleasure to be here and speaking with you and your audience.
That was Nima Golsharifi, CEO of NDB, a nuclear diamond battery developer based in San Francisco. Nima mentioned that the available nuclear material, if we recycled American fuel, could be 10 quadrillion joules. That would be about 2.7 terawatt hours of electricity, about what it takes to currently power our nation's electric vehicle fleet. I want to thank Nima for his time, as well as Georgi Gagokia at NDB for setting this up. You can find plenty of pictures for this episode on energy-cast.com, as well as on Instagram and Parler at Host Energy and Twitter at Host Energy Cast. All guests are sent the raw and completed audio the week of release. So far, no complaints. Be sure to leave us a positive review on iTunes. That gets the word out. Music was produced by Sean Stroop at Stroop Loops. That wraps up episode 140. Be sure to join us next week when we see how our energy mix is giving a new role to propane. Until then, I'm Jay Dowenhauer. We'll see you next time.